Okay, this week we will discuss on the general model of amplifier. Okay, so in previous class we have learned the fundamental or the basic theory and concept of the BJT. So in this week we'll discuss on how we can use BJT as amplifier, or how we can use BJT for amplifier circuit. Okay, so as mentioned in previous topic, so BJT based on the output characteristic of BJT, so shown as the plot of collector current IC against the collector emitter voltage VCE, against this VCE. This is output characteristic. Based on this characteristic, we can identify three main operating region. The first is the active region at the middle, and then we have the cut-off region where the current of the collector almost zero, and we have the saturation region where the VCE is very low, and then where the transistor will have the lowest internal resistance. Okay, and then it was stated in the previous topic that the suitable operating region for the amplifier application is active region. Okay, so we need to make sure that the VCE and the IC of the BJT is within this active region. So VCE, how we can control the VCE and IC value? This is by changing the apply voltages, and then if we use the resistor, we need to make sure that the value of the resistor is suitable, such that the VCE and IC as well as IB is within the active region. So take note, this is how we this is the very simple way how we can bias or apply the voltage at the transistor terminals, BJT terminal. Okay, BJT has three terminals. We have base, we have collector, and we have emitter. Okay, for this example, we apply voltage at the collector, so this denoted as VCC, and then emitter is grounded, and then we apply voltage at base terminal. And at collector, there is a resistor collector resistance RC. So usually this collector resistance, we need to add the collector resistance because one of the objective or reason why we need to have this RC is because we want to limit the current. If we apply VCC directly to the collector, so there's a possibility that of the production of high current, and then it will damage the BJT. So usually we need to have the RC. So this is the same reason for why we use the RB, base resistance here. And then this is the base resistance here. This is we use the variable so that we can control the resistance of at the base, and then we can control the base current, because at the output characteristic, this blue line is depend on specific base current. So by having this variable resistor here, we can change from 0 ampere to 10 microampere and 20 microampere of base current. Okay, so this is usually how we bias the transistor. Okay, so if you have this bias circuit, so how we can determine the VCE and IC? So since we have 15 volt here, but we don't apply directly, so VCE is not 15 volt. So one of the procedure to calculate to obtain the VCE and IC is by using the load line. So this concept of load line has been discussed in the chapter diode. So we use the load line, in order to get the diode voltage and diode current. So same with the BJT. So we need to plot the load line, and then from the load line we will get the IC and VCE. So this is the result is obtained based on the plot and based on the analysis. Okay, so the procedure to do the load line for the BJT is we need to do the KVL. We need to do KVL. So, and the KVL is for the current path from plus 5 volt until this ground. So this is the current path for the KVL. So in the equation of KVL, we will have IC and we also have VCE. So this is the similar to the these two parameter will fit to the right side figure or graph. So let's do the KVL. So KVL is minus 15 and then plus, so we have the voltage drop at 3 kilo ohms. So IC and then 3 kilo ohms, and then this is plus VCE. Okay, plus VCE, and then here at the emitter, although we have emitter current, but there is no resistor here, so no voltage drop. This is equal to 0. So based on this KVL, we can this is the equation for the load line. So we already get the load line equation. So next we need to plot the load line. So since this is a linear, the load line is a linear equation, so we only need 2 points to plot the graph. So they say this is VCE, and then we have here IC. So first consider when VCE is 0. When VCE is 0, the IC is equal to 15 over 3 kilo ohm. So this is 5 milliampere. So this is 5 milliampere. Okay, this is the first point. When VCE is 0, equal to 5 milliampere. Okay, so this is what we call it a saturation point. This is saturation point, or the maximum collector current. And then we also the next point is we consider when the IC is 0. So when IC is 0, so VCE is equal to 15 volt. So this is a 15 volt. Okay, this is the point here, and then now this point is called cut off point. So this is cut off point, means that the condition where the IC is equal to 0. Okay, again, the saturation point is the condition where the IC is the maximum. So we have the two lines, so we can connect these two points, and we can get the straight line. Okay, connect the two lines, and then we get the straight line. This is the load line. Okay. So the solution, or the VCE and IC is can be obtained by identifying the intersecting point. Okay, so this is the drawn this is load line. This is load line. So VCE and IC values are the value of the intersecting point. Okay, you can see there is many possibility of the intersecting point. The intersecting point is depend on another parameter, which is IB. Okay, IB. so it's IB. So if we can identify, if we know the value of the current base current, the actual base current, so we can identify the operating point. Okay, so this solution usually called the operating point, and we call it as a Q point. So Q point is the operating point. So this is the DC voltage of a current transistor with no input AC signal applied. So only purely a DC analysis. So let's say we consider the IBQ, the base current at the Q point. So this is a 30 microampere. So here 30 microampere. So we can identify the intersecting point. So the Q point is this is 1, 2, 3, 4, 5. This is 10, and then 5, 0.5. So this is around 6. Just put this is the VCE Q. Now I put the Q because this is the VCE voltage at the Q point is equal to 6 volt, and then the ICQ is equal to, okay, let's say this one is 1, 2, 3, 4, 5. Also 5, 0.2. Let's see, this is 3.2 milliampere. So this is the solution for the Q point.